Good evening, everyone. Welcome to the webinar series by IITACB. So as we all know, IITACB is established by IIT alumni from across all IITs to enable networking amongst IIT alumni and as well as to establish a collaboration between IITs and industries. So IITACB is also recognized body by MHRD. So for today's webinar, we have two speakers, Professor Apparao M. Professor Apparao is the Robert A. Bowen Professor of Physics in the Department of Physics and Astronomy, Clemson University, USA. And he is also the founding director of the Clemson Nanomaterials Institute. He is known as a physicist and a nanomaterials researcher. His contribution goes to developing Raman spectroscopy as a versatile tool for characterization of carbon nanomaterials. His current research at Clemson University focuses on energy generation and storage technology. He is the fellow of American Physical Society, American Association for the Advancement of Science, Material Research Society, and the National Academy of Inventors. And the second speaker for today's webinar is Mr. Rajat Verma, who is the founder and CEO of LOHUM Cleantech. Through high impact outcomes that significantly improve the environmental sustainability of batteries, he has led LOHUM to a recognition as the most innovative company of the year 2022, awarded by the Confederation of Indian Industry. And he, being a pioneer in the electronic waste management ecosystem, Rajat has developed several solutions across the e-waste value chain for markets across the India, the US, and the GCC. Rajat holds many degrees in engineering and computer science from IIT Kanpur, Stanford University, and MBA from Harvard Business School. So both the talks will be moderated by Professor Satish Vitta. So Professor Vitta is a professor in the Department of Metallurgical Engineering and Material Science at IIT Bombay. He obtained his PhD from University of Cambridge, UK. So during his career, he has received various prestigious fellowships, and currently he is studying the sustainability of materials for various applications. So along with Dr. Sushila Venkatraman, I'll be co-hosting today's webinar. And for audience, important announcement is please post your questions in Q&A box. So that will be taken up during the discussion. So over to Professor Rao.
Okay, good morning, everyone, and thank you for tuning in on a beautiful Saturday afternoon or evening. You could be doing many other things, but thank you for being here. And congratulations to LOHUM for the recognition. That's awesome. That's the future that we all need to really think about because the whole world is going electric. So with that brief introduction, and let me now try to share my slides here. Okay. All right, give me a second. Okay, you're able to see my slides now?
Yes.
Yes, we are.
Yeah. All right, so thanks for the invitation again. And so today what I want to do is to take a peek into beyond lithium batteries, what's in store for us. We know that, lithium-ion batteries are everywhere, and there's a good reason for that, because over the years, at least in the past 2 decades, there has been a tremendous improvement in the performance and cost of these lithium-ion batteries. For example, its energy density, right, at the cell level has increased okay, I'm trying to get my pointer. Okay. Yeah, so it's increased 3-folds, the energy density. The cost has decreased 7 times. So these are great, improvements in research and development. And that is the only reason why we're even able to think about electric vehicles or power tools, or even, the grid storage, right? Without these 2 improvements, there was no way we could have even dreamt about these technologies. So what is the primary reason? I think one of the primary reasons is graphite, which is cheap, and it is what we call an intercalation type of electrode. I'll have a couple of slides on that coming up later. and a lot of development on the oxides, on the cathode side, which is basically like layered oxides and the olivines and the spinels, and that has resulted in the Nobel Prize for John Goodenough, as we all know. So, notwithstanding all these progress, before it can reach everybody and globally, we have many potential challenges here. We need to continue to reduce the cost. And of course, one major stumbling block there is the finite reserves of some of the elements that go into these anodes and cathodes. And what you have here is a graph which is percentage mass present of these elements, lithium, sodium, and potassium, and percentage mass. And you can see there is a break in an axis here. So lithium is minuscule compared to sodium or potassium. And more and more countries are looking for lithium reserves. And in India, recently we have reports that Jammu and Kashmir and Rajasthan has found lithium reserves, and we are excited to know the quality of that and the utility of that. So, and the other challenge is we don't have a clear roadmap how to increase the energy density. What steps we need to take in a systematic, logical manner. And then the last challenge, there are more challenges, but on this list, the other last challenge is fast charging. And while we are fast charging, we want stable cycling and increased capacity. So how do we do that? So very quick video on this, how a battery operates. So basically, when the car is running and the battery is discharging, the lithium ions go back to the host, which is the cathode. And when it is charging, it does exactly the opposite. So this is your cathode, like the layered oxide, for example. This is your graphite, layered graphene structure that you see there. And there is a separator, and then there is an electrolyte. So it's a pretty complicated beast. I mean, there are so many different components that all have to work in sync. So that has been keeping the battery researchers busy. So let's take a look for a second, what exactly happens in the graphite, during the charging. So basically, the alkali metal ions go through a staging process. So this is called stage 3, where basically you have 3 graphene layers between the layers of the alkali metals, and then 2, and then eventually 1. And this is exactly what we want. We want more of the alkali metals actually interacting with the sheets of carbon so that you can get a much better performance, right? But in reality, in an electrode, what you have, if you will, these lines are these graphene sheets. You have a situation that looks something like this. So you have two obstacles here. One is diffusion. If alkali metals have to come to an innermost set of graphene layers, and then intercalation. So there are 2 processes that are fighting each other. So the question is, can we improve on this structure? So what we did in collaboration with Bing and Lu at Hunan University in China, we looked at tetraphenyl tin. We know that sulfur is a good additive in carbon research. So we adopted sulfur as a catalyst powder here in the powder form and annealed it to make graphene-like structures with a byproduct H2S and SnS2. And the basic reaction mechanism there is basically at high temperature, you have this singlet sulfur, which grabs the hydrogen, creates H2S and leaves graphene with you. So if you're familiar with graphene, you know that graphene, to grow graphene, you need a substrate like copper or nickel. And then the graphene grows on those substrates. And the Herculean task there is to separate the graphene from the copper, right? So we were also hoping to see some sorts of films on our substrates, like glass substrates we had used. But to our surprise, we saw under the SEM that our products look something like this. So basically, we saw graphene microspheres in there. And with electron microscopy, we found out that these are indeed graphene layers, which are radially sticking out from the center of this microspheres, which is actually an ideal geometry because there are a lot more, like if you see where my pointer is, there are a lot of graphene edges ready to receive the alkali metal during intercalation or during battery cycling. And if you do elemental analysis, this whole object is completely carbon, which is also very nice. So this is one leg up from graphite electrodes. And I have some data here to sort of show that. So if you look at any edge of these microspheres, again, you see many, many edges, like I showed you. And then if you do TEM, you can see it's actually a few layer graphene. It's not single layer graphene. And Raman spectroscopy and all other spectroscopies, you can see you can find all those details in the paper that we published. They have been reported there. So what is the proof that this is better than graphite, right? So one example is do the rate capability test, where you gradually increase the charging rate, which can also be expressed in milliamp per gram. So as you increase so first at low C rate or low current density, there is not much difference between graphite, which are these symbols here, graphite, or the few layer graphene. Okay, and that is understandable because slow C rate, there's plenty of time for the alkali ions to find their way into the anode. That's not surprising. But as you go to high C rates, you can see there's a clear, clear difference in the performance, and this is slightly under this. So the specific capacity of graphite for potassium-ion battery. By the way, this is the data for potassium-ion battery. Is about 272 milliamp hour per gram. Okay, so you're slightly under 2C here, and you can see the graphite has almost dropped to 0, right? And whereas the few layer graphene microsphere holds steady. And when you go back to slow C rate, the recovery is also very good. All right, so this shows that just by playing with the morphology of the graphene sheets or the graphite anode, you can get an improvement. So this is the first step, how you can make a higher energy density battery, if you will. And the beauty of this few layer graphene microsphere is it's not just unique to potassium-ion battery. It works equally well for lithium-ion batteries, aluminum-ion batteries, zinc-ion batteries, all. So this is a very nice material that is worth the chasing, in my opinion. So yeah, so the capacity goes low here for graphite because of this geometry. So to make sure that these few layer graphene microspheres are indeed robust, we opened up the cell after cycling, and sure enough, they have high specific surface area because of the covalent carbon-carbon bonds. They are pretty robust, and you can use them any number of times. And here is one data set here, again, for the potassium-ion battery, where you see that the commercial graphite rapidly tends to fade in capacity, and the battery dies here. And same is the case if you make an electrode out of commercial graphene. But the sheer geometry of this microsphere allows it to go to 1,000 cycles or more. We have gone as high as 10,000 cycles, and that data again can be found in this reference. So how does it compare to what's out there with regard to other forms of graphene? Graphene oxide is a material that many researchers have worked on because that it can be scaled more easily than graphene, because graphene, like I said, you're stuck with the substrate. So this graphene, the few layer graphene actually outperforms all of them as far as we can tell. And so we are up here in terms of capacity retention as a function of cycles. All right, now, so this is an example of an anode where by sheer improvement in the morphology, we could increase the energy density at least twofold, threefold, right? Now, if you want to go even beyond that, right, then we have to actually shift gears completely. We have to work with something that are called phase transformation electrode generally, or more specifically, they are called the alloying type of anodes and the conversion type of anodes. And they are shown in this figure here in the schematic. So silicon falls here in the alloying type of anode, and you can get capacity, silicon's capacity is close to 4,000, right? Pretty high. And sulfur and sulfides, phosphides, oxides can also give you high specific capacity. And I'm going to talk about sulfides here for today and not talk about the other things. So let's consider silicon first. So although the capacity is pretty high, there are numerous challenges, and I'm showing two of them here. Is that, you know, you cannot, so definitely silicon, you have to blend it in with graphite. And the industry preference is to try to stay below 10%, 10 to 8% of silicon. And the reason for that is because silicon, upon cycling, goes through a volume expansion and contraction. And with many, many cycles, basically it undergoes pulverization. The whole silicon disintegrates, and the pieces of silicon don't even communicate with each other. So that's one problem. And if you are familiar with the solid electrolyte interface, which is formed in the initial cycles, then tends to break. And then each time the solid electrolyte interface has to be formed, which means you're not using your active, you're wasting your active materials, because some of that and the electrolyte molecules end up in the solid electrolyte interface. So that's one main problem there. The other problem is delamination. So people have started, again, just like the example I gave you with playing with the morphology, people have played with the morphology of silicon. They have done silicon nanoparticles, silicon nanotubes, nanowires, nanocoils, you name it. There are very smart people who can make these materials and put them in electrodes and test them, but none of them works very well. So what we did was with Professor Shrikant Pilla and Mortaza Sabat here at Clemson University, we basically went back to the drawing board and used a green synthesis method to sort of come up with this kind of a structure, which we call silicon nanoquills. This is actually a silica nanoquill, what you're seeing in the image. With Mg reduction, you can make it into silicon nanoquill, which has similar morphology. So you have porous, nice porous structure, hollow arms. And if you compare the cycling of that with, for example, silicon nanoparticles, so this is specific capacity versus cycle number, it holds steady. And this is work in progress. Still, we haven't published these results yet. We have to tune the binders, we have to play with the substrates or the current collectors and so on and so forth. But then, nonetheless, these results were promising enough that we went ahead and filed a patent on this one. So more to come on this probably some other time. So these are the two anodes that I wanted to just give you as an example, that where morphology can actually take you a couple of steps or increase your specific capacity. Now let me switch gears and talk about two examples of a cathode. So one cathode which you're seeing on the screen is sulfur-based, and this is related to lithium-sulfur battery. And the other one that I'll talk about has to do with a potassium-ion battery. I'll come to that later. So lithium-sulfur, again, lithium, as we saw in that plot on the previous slide, sulfur has high specific capacity. So why not use it? So the problems or the challenges there is that sulfur is insulating. So you need to have some sort of an additive and some sort of a binder and fashion it into an electrode and then pair it with a anode, either lithiated graphite or lithium, and choose proper electrolyte and separators and so on, right? So the main problem there is that if you use elemental sulfur, which is a crown-shaped molecule, it's an S8 molecule, it undergoes a lot of what we call the polysulfide shuttle. It forms different compounds during discharge, and this is reversible. It goes back here. And the problem, though, here is that a lot of your active material is tied up in this polysulfide shuttle. You're losing lithium, you're losing sulfur, and you don't get the full utility of the sulfur that you have here. And there are other problems, side reactions and so on, which then lead to capacity fade, right? So again, this is work with Bing and Lu in China. So one idea is to move away from sulfur and use what we call sulfurized polyacrylonitrile. So basically PAN polymer, you sulfurize it and then you make an electrode out of it. And that we found can help mitigate this polysulfide shuttle because there is no more elemental sulfur in there. And Raman spectroscopy and other tools have also shown that, okay? So this is, again, now we are actually replacing the basic element here from sulfur to sulfurized polyacrylonitrile. Okay, so but we also found that this alone is okay, but we can do better. And we can do better in terms of electrolyte engineering. So what I show you schematically here is that cathode, and let's say this is elemental sulfur or any sulfur species like SPAN, and your anode here, with traditional electrolytes like carbonate-based and ether-based electrolytes. I'll show you more details on the subsequent slide. What is known is that these electrodes, they disintegrate over many, many cycles, and there's dendrite growth on the anodes and so on. So what we need really is a new engineered electrolyte so that you can get what we call the bilayer SEI. So bilayer SEI is this black outline that you see here on the cathode and the anode side. That way, then with many, many cycles, you have very stable cycling and a battery. So how do we develop this new electrolytes? So let's say we start with two traditional electrolytes, TE1 and TE2. And our rationale was very simple. You have electrolytes, you have salts. Why don't we start mixing and matching these salts in these different electrolytes? It's a brute force method, and we actually looked at 60 different compositions, and we found some compositions that do support this bilateral SAF formation. And the batteries that we made out of these actually show good cycling. So here I'm going to walk you through very quickly, what all options we have. It's a complicated problem and a nice platform for artificial intelligence, machine learning to help us find appropriate electrolytes that can give high performance batteries. So as an example, I show you here, traditional electrolyte one is LiTFSI in DME and DOL, and traditional electrolyte two, which is LiPF6 and these solvents here, right? And so this electrolyte is known to form a unilateral SAI on the anode. This favors forming SAI on the anode, while this favors forming SAI on the cathode. So we started mixing them. Like this is an example, 1 molar, a little bit of this salt here, a little bit of this salt here, and in all these different kinds of solvents. And again, you have a lot of variety here. You can do 0.1, you can do 0.2. But because of, we were doing by brute force method, we just did 60 electrolytes. Of the 60 electrolytes, we found that Ne2, which is this composition here, LiTFSI and ECDMeDOL, does a fairly decent job for a lithium sulfur battery. This is not to say that this is the end all for this problem here, because I think with machine learning, you can probably find even better electrolyte for lithium sulfur batteries. So how is it better? So here I'm showing you capacity versus cycle number for the traditional electrolytes, which is the black trace and the red trace. And you can see capacity fades here because these are unilateral SEI. And the new electrolytes that we found, Ne2 does pretty well. And I know I'm going very fast here, so because of time constraint, but if anybody wants to visit more and learn more about it, this is a reference for the how we have engineered this electrolyte. You can understand all this in terms of HOMO-LUMO and so on and so forth. Okay, and so here is another example of now, running at a pretty at 1C rate and using the new electrolyte composition. So here is an example of one where we are cycling, it holds pretty steady right here, whereas with other electrolytes, it suffers a capacity fade quite quickly. And this is pretty good. I mean, this is already, this is 600, so about 650, 700 level of milliamp hour per gram. So this and a lot more work is needed in this area. The Biden-Harris government recently encouraged a lot of battery researchers to look at this, because if we can nail the lithium sulfur, definitely we could now be going from electric vehicles to aviation technology. Have small planes fly on battery powered energy. So that's where this field is heading. Okay, now a slight digression from the main topic here. So this is still has to do with SPAN, sulfurized polyacrylonitrile. But we thought that, we had an opportunity to collaborate with Professor Srikant Pilla and researchers at USDA, Department of Agriculture. And one of the things is that, there's a lot of interest in wood-based or agricultural-based, broadly speaking, materials for energy storage. So the nice thing about the plant, nature makes natural morphology, right? Natural morphology for the tree. So this is a piece of a balsa wood where the porosity, the inner guts is such that it can draw its nutrition naturally in the tree direction, right? And so if you look at it in the transverse direction, you'll see this beautiful porous structure there. So can we use something like this, green material as a current collector? So we fashioned these into current collectors, made thin slices of them, carbonized them. Actually, first delignify the wood. This is delignified wood, then carbonize it, and then coat them with SPAN. And then if you do electron microscopy, you can see sulfur is uniformly present everywhere. And this carbon and oxygen is also quite uniformly present. And if you look in the longitudinal or the radial direction, also you can see very uniform distribution of these elements. Okay, so how does this function in cycling? So here is an example. The capacity is pretty respectable. It's 1500 milliamp hour per gram, and over 500 cycles. But of course, this is at low C rate, and more work needs to be done to see how this can perform at high C rates, and how they perform as a pouch cell and so on. So this is an active area. All right, so this is, again, morphology is helping make us better electrodes. So now, completely, if we move away from lithium, in the periodic table, right below lithium is sodium and below sodium is potassium. So why have we skipped sodium? So this is work again with Bing and Liu. Not that because we don't think sodium is a good competitor, but there's already a lot of work with sodium. So we decided to go even one rung lower and start looking at potassium. And what you're seeing on the screen here is gravimetric energy density versus volumetric energy density. And the attractive part of potassium is that its reduction potential is closer to that of lithium than sodium. Sodium is 2.7 compared to 3.04, whereas potassium is 2.93. So that helps. And then again, we already talked about the abundance. Both potassium and sodium are abundantly present. And the other neat thing is that there is this solvation shell that forms, and there is the Stokes radius and all the other dynamics that takes place for the ions, alkali metal ions in the electrolyte during operation. And it is known that in certain solvents, potassium, like propylene carbonate, potassium has very high ionic mobility, which means it will help in fast charging. Even molecular dynamics simulations support that view, that diffusion coefficient is larger than that of lithium. And when you think about the commercial angle, there is no need for copper current collectors. Unlike lithium-ion batteries, you need a copper current collector for anode. Here you can do away with that. So you have reduced weight, reduced cost. But again, there are numerous challenges. Potassium is very reactive, can cause fires, dendrites. And because potassium is the third element in the alkali metal column, when it intercalates and deintercalates, the d-spacing between the graphene layers is pretty huge. And so this cartoon actually captures all the different challenges that one has. So you have to solve this problem with a global perspective. So I want to talk about one example here about the Prussian blue cathodes, right? Like the lithium-sulfur cathodes are attractive for the lithium-ion battery. The Prussian blue cathodes are attractive here because they're cheap. And here is a schematic of its framework. It has an open framework, abundant interstitial sites, right? You can put a lot of alkali metal in there. But the problem is that during charging, when the alkali metal leaves the host, there is a dissolution of Mn. For example, these are Mn right here. This is Mn. This is potassium here. And basically, you're left with a vacancy. So Mn tends to dissolve, and it creates this vacancy. And as a result of this vacancy, when you again try to, lithium tries to come back in, then basically it leads to instability in the structure, and the cage breaks down, or basically the electrolyte starts breaking down. So what is the solution here? The solution here is, what we found is, again, this is work with Bing and Liu, is that when Mn dissolves into the electrolyte, can we have something else come and stick here so that it stabilizes the structure? And we found that the electrolyte engineering for this problem here is to add a little bit of a ferric sauce. So we have ferric ions, and when potassium tries to come back in, like here or like here, instead of breaking the cage, what happens is when this comes in, this also lodges in, and stabilizes the cage, and you don't have any more problems like you see here, right? And as a result of this, we could cycle this electrode 130,000 times. So that's a huge number. I mean, now people are also saying that if we have this kind of breakthrough, then we can stop thinking about supercapacitors, because that's the beauty of supercapacitors, right? Supercapacitors, you have many more charge-discharge cycles than compared to the battery, because it's all Faradic processes there, right? So, but batteries are can compete very well even with the supercapacitors when you have the right kind of electrolyte or the electrode engineering. Okay, so let me show some details about this this particular cathode for potassium-ion batteries. So I'm going to refer to this as KMNF, and how we can improve its performance in a modified electrolyte. So what is the electrolyte here? The electrolyte is basically this one here. So basically it has a potassium ion, and then it has the CF3 right there. This is CF3, this is SO. These are the SO3. And like I explained with that previous cartoon, when potassium leaves, you have structural disintegration. But what is the ferric source? The ferric source is has similar moieties as what you have in the electrolyte, but it has an ion atom right there, and that tends to stabilize and prevent degradation of the structure. So let me show you some data for that. So here is a full cell where we have the KMNF with the modified electrolyte. That means we have the ferric source in there, and the PTCDI as the other electrode. And the reason this works, in addition to making or stabilizing the structure, is that the ion, the ferric, also participates in the solvation shell. So this is the pure electrolyte. So this is the CF3, the SO3, and so on, like I showed on the previous slide. The green atoms are the potassium, right? You're forming a solvation structure here. And here is where even the ion is present in the solvation structure. So again, if you compare to what's out in the literature, this shows up over here, pretty high in performance. And you can cycle it at different temperatures. You can cut the pulse cell, it still continues to operate. Okay, in the last few minutes that I have, I'm going to now shift gears and talk a little bit about what we are doing with the industry. And since LOHUM is represented on this talk here, I thought I'll say a few words. I cannot say too much about this work because we are under an NDA with the company. So basically the idea is that, batteries in electric vehicles or grid storage, they go bad. And once they go below 80% of their capacity, then they have to be basically replaced. So we were given these modules that you see in this image to first tell the manufacturer what went wrong without even opening up the module, which was a challenge in itself. But we could tell them what was wrong, whether it's the anode or the cathode or the electrolyte or the separator. We did that. And then they green signaled us to go ahead and check, one level deeper. So we opened up the modules and we are actually doing some pouch cell testings. And the hope is to fix at the pouch cell level and not go any deeper. The recycling business right now, basically they go even one step deeper. They have to take these pouch cells apart and try to salvage all the useful elements, right? So we are hoping we can turn around after this and go back to making modules and test them at the pack level. So this is one effort that's going on. in our lab. And the other effort, like the delignified word, for activated carbon in supercapacitors, right? Activated carbon, the source for activated carbon right now is coconut shell. And it comes from, again, there are, geopolitical issues. It comes from specific countries. And then it is processed in China, and then it's distributed globally. So there are companies this is work done with these two companies here, Ardent Mills and Kyocera AVX. They want to actually shift this, paradigm. And so we are looking at wheat-based products, carbonize them, make slurries, as you see here, make coatings, and put them on electrodes. And right now, these materials that we made are being tested for supercaps by AVX. So this is another project that's ongoing. And to handle all these federally funded projects and the industrially funded projects, we are now at a point where Army has stepped in to actually help us build a dry lab. So this is a schematic of a dry lab that we are currently building. So this is a glove box, 2-user glove box, and the different things, vacuum oven, the heating, rolling, all the way to making a pouch cell. All the equipment is going to sit in here. So that's in progress. So how much time do I have? Satish? Okay, so maybe I'll take
5 minutes or so.
Okay, perfect. Then I will talk about translating technology to the industry. The technologies that we developed in the lab, how can we translate it to industry? I'll give you one example. So back in 1999, a long time back, we came up with a process where we could actually grow carbon nanotubes a very economical way. Prior to this work, those are familiar with carbon nanotubes. First of all, we know that they can make excellent electrodes for supercapacitors, batteries, whatnot, right? Touch screens and so on and so forth, because of their high electrical conductivity, thermal conductivity, and their mechanical strength is amazing. All great high attributes of carbon nanotubes. So before this work, there were two methods. One is to make carbon nanotube with electric arc. You basically have two graphite rods that you strike an arc in between them. And one of the electrode will have the catalyst, and that electrode will be sacrificed and converted into carbon nanotube. It's a very high energy process. That's the problem. And it's a highly non-equilibrium process. You make a lot of junk. So you have to do chemical separation, chemical purification, blah, blah, blah. A lot of steps before it can be used by industry. And then the other method that was well known before our work is to use high power laser. And that also has similar problems. Okay, so again, it's energy intensive. It has crud in it. We have to do the separation, purification, so on. So we thought of actually going back to the drawing board and seeing what exactly is needed for making carbon nanotubes. All you need is a catalyst that has nano dimension, right? And then you need a carbon precursor, because that's how the carbon fiber industry has grown to what it is today, right? So that's the basic idea there. So we took ferrocene, which is very cheap, because it has two pentagonal rings with an iron atom sandwiched in between, and at high temperature, like so not so high, around 200 degrees centigrade, you can actually decompose that, and you have iron atoms. And if you have enough of these iron atoms, they will actually come together to reduce their energy and give you a nice, beautiful nanoparticle, right? So and then what about the carbon precursor? We could use gases like methane and so on, but methane, you have to go up to at least 1,000 degrees centigrade to decompose it. So we said, well, rather than putting ferrocene in a boat and passing methane, why don't we find a solution in which ferrocene is readily solvable? And we could use benzene, but benzene is toxic. Xylene is also toxic, but less toxic. So we zoomed in with what we call the ferrocene xylene method, and we put it in an injector, and we basically shoot it into a preheater, create your particles here, and then there is argon jet that pushes everything into this hot zone. This is around 700 degrees centigrade, and you can make beautiful oriented growth of carbon nanotubes on silicon substrates, on glass substrates, and so on. In our original design, we thought we will collect them over here, but there was no need for this. So we got rid of this in version 2.0 of our setup. So I'll show you an example of an SEM. So here is an example. Again, the details can be found here. There are a lot more images in that paper if anybody wants to check it out. These are oriented carbon nanotubes, very easy process with quite high purity. The trick is to control the injection rate and the flow rate and the temperatures, obviously. All right. So like I said, these carbon nanotubes, people have thought long time ago, 2004, 2008, 2010, that it has a lot of value in energy storage devices. You can take these carbon nanotubes, use them as is, or you can actually fashion them into a paper, which is called Bucky paper, and so on, okay? So let me show you a quick video of how this actually works in the lab. So this is the furnace. There is the preheater is right here because the furnace has a gradient. So if it is 600 degrees here, it's about 200 degrees at the edges. And this is our injector. This is the ferrocene xylene liquid in there. You will see it when I zoom in. And in this setup, what we did was we actually made the substrate rollable. So this is a roll-to-roll process. So you no longer have to do batch processing to make nanotubes. You can do a roll-to-roll process. And so here it goes. So what you do is you take a kitchen aluminum foil, and then these are your mass flow controllers that control the gas flow. That is our injector, and that is your ferrocene xylene liquid in there. And as the aluminum foils rolls in and out of this hot zone, you can see that after a while, you get nice black coating on the aluminum foil. It's coated on both sides. And this can be used directly for electrodes in supercaps batteries, for example, right? So this is a very nice technology that actually was conceived in academia, and then the students who were working on this projects, who helped develop this project, one of the student had a streak of entrepreneurship in him. So he went ahead and started a company. So what you're seeing now here is before and after coating. Okay, so they started a company called Nanotech Labs, and they basically scaled up this process. And so it went from TRL 3 to TRL 6 with the help of this Nanotech Lab. And in the process, we developed several patents came into existence. And then now what this Nanotech Lab has actually created another division called Buckeye Composites, which is a division of Nanotech Labs, where what you're seeing here is again a roll-to-roll assembly process. So you have sheets of carbon nanotubes, and this, if you will, this is your separator, and so on, right? So this is a great example. This is TRL 10 actually, because they are also making other composite structures for the defense purposes. So I just wanted to take about 3 minutes, 5 minutes to show you that what has been developed in the lab through the help of your students and through the help of your IP office can be very well translated to the market. So I think that's my last slide. So to summarize, the world is going electric, but we need to go beyond LIBs because there's not enough LIBs for everything. The potassium-ion battery would be ideal, or like sodium-ion battery would be ideal for grid storage. There's no need for using lithium-ion batteries there because it's not mobile, right? The grid storage is stationary. I showed you that how morphology can play into improving energy density, cycling stability, so on, both for the cathodes, both for the anodes. And I showed you how with the industry, we need not go all the way to ripping the battery all the way to its pieces. There are other strategies one could look at. And then I gave you an example of agricultural products or agricultural waste, how they can be harnessed into supercapacitors or active materials for energy storage. So I want to thank my collaborators, Bing Lu and his team at Hunan University, China, with which we have very nice collaboration. The Clemson team, and then my collaborator at USDA. With that, thank you very much, and I will be happy to entertain any questions. So I would turn it over to Professor Satish Vita to do the needful.
Well, thank you very much, Apparao. It was a nice presentation and giving an overview on all your research activities in the area of lithium-ion batteries, or I would not want to call it as lithium-ion batteries because you're looking at something more than lithium or sodium and potassium too. So it was very nice to see that there is a lot of work that is going on in the laboratory in order to shift away from lithium-based systems to sodium and potassium. So that's very heartening to know that you're moving away and there is technology that is being worked or developed in this particular area. So just a few comments I'd like to ask. In the case of these lithium-ion batteries, you were talking about graphite as an anode system, correct? So you were talking about opening up this particular structure in order to increase the specific surface area so that you can enhance it. If I look at it without using this particular technique of opening up the structure, what is the percentage loading that takes place in commercial materials, for example?
Okay, and commercial materials, of course, they want to go as high as possible. So I don't know the exact number, but the problem is you can actually use the doctor blade and put as much active material as you want. But then you run the risk of delamination. The whole active material can simply peel off.
Okay.
Right? So what the industry does is they actually use another step called calendaring, where they actually take the current collector, make a slurry of desired thickness, and then they calendar it down to very thin layers, so that it's packed very tightly. And therefore, when you put this current collector either in 18650 cell or coin cell, not much volume is taken up by the active material. It's pressed down to a very thin film. So the name of the game is to try to put as much as you can, and you run into a limit. But I don't know the exact standard, exact thickness they go up to.
Okay, because I just wanted to know how effective in terms of realization of the technology will be in order to open up, because to do that opening of the graphite, also you need to spend some chemicals and energy in order to open up that particular structure to get higher specific surface or area for that matter. So that was just now with respect to silicon nanoquills, is it going to be scaled up, or is it feasible to scale it up to large quantities?
Yes. With the nanoquills, whenever we presented at the ECS meetings, Electrochemical Society meetings, there's a lot of attraction. One of my colleagues at Georgia Tech, he has actually started a company called, it's basically uses silicon-based anodes. It's called SILA, S-I-L-A, SILA Technologies. They always come talk to us about scaling up. So we are looking for entrepreneurs who are willing to, take this to the next level. Right now, it is still at the lab scale. It is not at the pilot scale. No, not there yet. But it is doable because everything is green process here.
Okay.
We are using nanocellulose as one of the ingredients, which is plant derived.
Okay, so when you said silicon, is it pure silicon that you have to use in this system?
No, I was referring to silica nanoparticles, silica nanoquills, silica nanoquills, the one that I showed.
Okay,
so,
yeah, but I was referring to the sealer that you mentioned.
Oh, yeah, it is proprietary. We don't know what form of silicon they have discovered.
Right,
So
because they put a demand on the silicon purity and what kind of silicon is required for this activity.
That is proprietary. They never divulge that information in their presentations or their website. So we don't know what kind of silicon they discovered. So it is definitely different from nanoparticles, nanotubes, and nanobells, and all these other forms. Yeah.
Yeah. So I had one quick comment, or rather a question regarding the potassium work that you have been doing.
Sure.
So did I read it correctly that the capacity when you constructed a full cell that came down from about 1500 amperes per gram or something to about 150?
Of course, yeah, because you're limited by your. Oh, let me plug in my charger. Give me a second. Sorry about that.
Yeah.
Wow. Yeah, so you have, I mean, it depends on how you pair. Yeah, you're pairing with another anode, which does not have infinite supply of potassium, unlike a potassium, current collector, for example. So it is normal that when you make the full cell, when you test the half cells, you will get much more capacity, and when you make the full cells, it'll be lower. Yes.
Okay. Okay. There is a question from one of our audience here. It's a very interesting question. When can we expect potassium-ion batteries in the market?
Okay, that's a very good question. I would say probably about 5 more years, I think, because not because potassium-ion batteries are not doing well. The problem is that everybody is so much hung up with lithium-ion batteries, and that is the thing. I mean, I'll give you an example, right? I mean, let's say you have solar panels on your rooftop, right? And the energy is stored in lithium-ion batteries. And in my opinion, that is not the most prudent way to do it. Potassium-ion batteries can do the job equally well. You just have a bank of potassium-ion batteries sitting in your backyard, right? Or on your rooftop, or your terrace. But they don't want to think that way yet, because I think we are discovering more and more lithium. And people are willing to pay the extra price. But there will be an inflection point, I think, at that time, probably, I would say about 5 years, because now some industries are looking at the sodium-ion batteries for e-bikes, for example.
Okay.
You definitely don't want to use sodium-ion batteries to drive your car. You will need many, huge battery packs. For a bike, sure. Auto rickshaw, sure. So that market is growing. So I'm predicting 5 to 6 years.
Okay, so the time for a last comment that has been made. There is huge effort on storage of lithium and cobalt from conventional reserves. People are talking about recovery of lithium battery components, which Rajat is going to be talking about. And there is a comment that, as you said, the fascination with lithium will linger for a longer time than what is ideally probably required. So this is just a comment somebody has made that with recycling coming in, the fascination with lithium batteries will stay for a little longer compared to introduction of potassium batteries. But probably you're very right. I think for stationary applications, you don't need to use all your lithium. You could as well do with heavy or huge masses of potassium or sodium batteries for that matter, when you want to use them for solar power generation, storage, or something of that nature. There is a comment regarding activated carbon. Can automobile and power plant exhaust be harvested for activated carbon?
Say that again, sorry.
As far as activated carbon is concerned, so there is a question saying that can automobile or power plant exhaust be harvested for activated carbon?
Yeah, but it will not be of high enough grade for devices like supercapacitors, because even supercapacitors, they have a particular benchmark. They target a specific volumetric capacity, which the exhaust, the carbons found in the exhaust fail to deliver.
Yeah, but I mean, give me the liberty of partly answering that particular question.
Sure.
If carbon that is coming out from your automobile or power plant exhaust, it's a very inefficient combustion process that is taking place in the system. So I think it's more important to take care of the combustion rather than be worried about getting activated carbon from these particular exhausts, I would say. What do you say?
But
if carbon is coming out from the engine.
So there are a lot of smart people I know, unfortunately or fortunately. So they are taking this combustion engine, and basically by combustion, they are now making graphene, which is mind-boggling to me. How by controlling the feedstock and other parameters. So who knows? It just takes one such technology to show that a forward reaction is highly favorable and cost effective to change the game. We don't know.
Okay, yeah. With that, I think if there are more questions or comments, we'll take it up at the end of the session. So I can give it to Rajat for his next presentation.
Thank you.
Thank you.
Thank you, Professor Satish. Thank you, Professor Rao, for that very inspiring presentation. And I'm sure everyone's technical juices have gotten flowing after your presentation. And I think a lot of new opportunities probably have emerged, or new areas of interest for a lot of folks who are in this audience would emerge. Certainly for me, and certainly I can speak for my organization, we would be very curious to understand the potential in some of these areas of research that you are conducting with your partners. What I would like to do over the course of the next 15-20 minutes is hopefully get your business and commercial juices going. So talk a little bit about what we are doing in the industry, talk a little bit about what is happening in the recycling industry, and then talk a little bit about the specifics of what we are doing at LOHUM. So I'll start my presentation with your permission, Professor Satish.
Yes, please. Please go ahead, Rajat.
Can you folks see my screen?
Yes, it's very clear.
All right. So good evening, everyone, and good X to everyone who's joining from some other part of the world. I represent LOHUM. I'm the founder and CEO of LOHUM, And we are in the business of producing energy transition materials, primarily through sustainable activities. Recycling is the core of organization. We also carry out a bunch of other activities, which include repurposing and what we call low carbon footprint refining activities. I'll give you a little bit of information on what is happening in the recycling industry at large. But before I go there, it's important to understand, and a lot of my presentation will be focused on understanding the commercials associated with the battery recycling industry. So if you look at a car, I think everyone here knows, or if you look at an EV, I think most of you probably by now know that battery is the most expensive component of an electric vehicle. And when you actually break down the cost of a battery, it's really about the cell which goes into making the battery. And a cell is primarily all about the materials that go into making the cell, of which, as of today, the cathode material is the most expensive component. These materials are linked to the commodity markets. The materials that go into making the cathode are used not just in the battery industry, but also in other industries such as pharmaceuticals, aerospace, steel, so on and so forth. So there's a commodity pricing that is associated with these materials, and the commodity price determines how expensive and to what percentage of the overall cost structure of the cell is the cathode material all about. But broadly speaking, you get a little bit of a breakup there, and cathode material, particularly when the commodities have a bull run, can be as much as 50%, if not higher, of the overall cost of the cell. The anode material tends to be a little bit cheaper. And then, there are separators, electrolytes, etc. And a lot of you probably got a lot of information from the earlier presentation from Professor Apparao. When you look at the cathode material itself, or when you look at the materials in general itself, you've got lithium, cobalt, nickel, and graphite. The percentages that you see in the screen in front of you are largely representative of what is happening in the industry today. So we've got various chemistries of lithium-ion battery or lithium-based batteries, ranging from lithium-ion, the traditional lithium-ion battery that initially came into the consumer electronics segment was what was known as the LCO battery, which had a lot of cobalt content in it. Then we graduated to NMC batteries, which had a reasonably high nickel content to it. And then today we are living in a world where we have a very large, very strong content in terms of nickel and relatively low content in terms of cobalt and manganese, which are the other two elements which make up the cathode structure. Lithium also tends to be present, typically not in very large quantities. Lithium typically is, as Professor Rao had explained, it is there on the hosted by the cathode and shuttles between the cathode and the anode during the course of cycling. And then typically it's also present in the electrolyte. LiPF6 is typically the electrolyte of choice, which is used today. All these things are undergoing changes, but this is what you see broadly in the material in the market today. So since battery materials are indeed the most critical cost items, and by most measures can make up almost 40 to 50% of the bill of material of an electric vehicle itself, what is going on in this battery materials value chain? If you look at the value chain, it can be split into the categories that you see on the left-hand side. You've got mining companies, you've got companies with battery materials, you've got companies that manufacture the cells, you've got companies that actually assemble the battery packs, either for electric vehicles or for energy storage on the stationary side. And then you've got recyclers who recycle the batteries and move them back into the refining process. Or if not directly extract the material, move them back into the battery packaging process. And then if you look at the broader ecosystem, since I largely believe we've got an Indian audience here, you've got India, China, and rest of the world as my next three columns. And broadly, India is highly competitive. There's I should refrain from using the word highly competitive. It has a very strong competition on the battery packaging side. China, of course, has the same. Rest of the world also has the same. That's the simplest part of the value chain. How to assemble batteries given various cells. The more difficult and the less intense parts of the value chain tend to be the other things that you see both on top and at the bottom of battery packaging. But China actually has got it all figured out, right? It's got control of mining. It has got refining. It knows how to get the battery materials. It knows how to manufacture cells. It knows how to assemble packs. It knows how to recycle. It knows pretty much everything. So what this should help you think is what is going on geopolitically in this ecosystem. That brings me to a little bit about the value chain again, in terms of how do capacities come up in this value chain. Again, if you look at mining, that tends to be the longest capacity addition activity. If you're very lucky, you can probably add mining capacity in 5 years, but it can go up all the way to 25 years. Environmental permits, capital, raising finances for your mining activities, all things can take brutally long time. Chemical processing, relatively easy, but most people will indulge in chemical processing only after they've got the raw material tie-up. Cathode production, a little quicker. Cell manufacturing, much quicker. Application engineering comes down to you actually testing out your application for the final product out there. So given this scenario, typically it's very difficult to get supply in the market of whatever material that you're thinking about. And because of that, there is, at least for the foreseeable future, going to be a huge demand-supply mismatch.
Rajat,
yes, Sushila.
Your voice is sometimes breaking a bit. Would you mind? Maybe you could just turn off the video.
I've done so.
Okay, please go ahead.
All right. So, again, like I said, mining activity is the longest lead time activity here. And mining can actually result in undue pressure on the supply side, which consequently tends to keep the pricing of these materials very high. If you look at what is going on today across the value chain, again, I think no surprise, China controls bulk of the value chain, whether it is on sourcing, refining, cathode, anode production, or battery cell production. If you look at most of those numbers, they tend to be extremely high for China, ranging anywhere from 40% to 70%, or if not even much higher numbers across the value chain. So how does the rest of the world effectively compete as they move towards energy transition, as they move towards their desire to bring down their carbon footprints, as they move towards their own goals for electric vehicles and energy storage? Sushila, is the voice a bit clearer?
Yes, it is better.
Thank you. Now, mining itself is not a very sustainable activity. Broadly, there are large problems associated with mining. There are humanitarian crises associated with mining. People tend to get displaced. People tend to be poorly compensated. There are environmental pollution activities associated with mining, both with the digging up and the tailings that mining leaves. And there are undue and significantly large resources that get associated with mining, particularly when it comes to water, chemical, and power. So how does the world truly transition to low carbon? Because we are doing all this because we want to create a sustainable ecosystem. And if the very basis of a sustainable ecosystem is something not very sustainable, then are we doing justice to what we are trying to achieve? With all that in mind, we do believe that battery recycling or a circular economy for batteries is super critical. A circular economy lends several different advantages to what mining cannot. To begin with, it has a significant lower humanitarian impact. Battery recycling companies are independent of where people stay. They can be set up in industrial areas. They can be set up without exploiting the existing ecosystem that exists in any particular geography. It has a lower environmental impact. Various studies suggest that EVs in general have a net positive impact of 225 kilograms per carbon dioxide equivalent per kilowatt hour of battery produced. With recycling, you have an additional saving of another 10%, if not more. And with reuse, you have an additional saving of approximately 30%. You tend to save a lot more water in the process as well, traditional mining activities. And per our calculations, you're seeing almost 100 saving on a per kilogram of material with mining activities. So clearly, it helps us achieve our greater goal of carbon neutrality. There is a geopolitical component here. As my previous slide had indicated, a lot of the mining world and a lot of the battery materials work is controlled by China. No one in the world wants one country to dominate the entire value chain. But the good news about recycling is once the material has entered your territory, it can stay almost infinitely in your territory. So this allows different countries to actually secure their own resources and then use those resources to, play out their own green strategies. And finally, I think a little bit of this was referred to by Professor Apparao as well. Raw materials are scarce, right? Lithium is not that abundant. By some calculations, we are expecting to use almost 4 million tons of lithium carbonate equivalent per year in the next 7 to 8 years. And the known reserves globally are barely 70 to 80 million tons of lithium carbonate equivalent. So you're talking about broadly a 20-year time frame before you run out of resources. And needless to say, a lot of these resources are not very viable. If you start using these resources, which typically tend to have poor quality ores, so poor quality brine, then you probably will be increasing the cost of your battery and thus of your vehicle so significantly that it will harm the overall ecosystem. So from all these four broader perspectives, recycling becomes super important. Now, how large is the recycling problem, right? Elon Musk made a very strong commentary recently that we need about 300 terawatt hours of battery installation to truly transition to a clean and green energy environment. And then different folks, different analysts have put out their own estimates of how this transition is going to happen. And we look at various scenarios. And then when you see what the world is expecting, this is extremely mind-boggling. We are talking about almost 7 terawatt hours of battery, which are needed by 2030. And we're talking about 20 terawatt hours of batteries needed by 2050. Compare this with what we have today. Last year was the first year that we hit a number close to a terawatt hour. About 800 gigawatt hours of batteries were manufactured globally. We're talking about an astonishingly large growth rate. And that astonishingly large growth rate results in an astonishingly large capacity that we need from a recycling perspective. If you look at, so we broadly think recycling capacity needs to come online about 8 to 10 years after the primary capacity. And so if you look at some of the forecasts that we make, we're talking about approximately 100 million ton capacity needed by 2060 to ensure we recycle everything that is present in the world. Now, some of these numbers have to be taken with a pinch of salt. Professor Apparao has demonstrated very, very effectively that energy densities are going up. We are sitting today broadly in the 250 watt hour per kilo energy density. If some of the interesting technologies evolve, we could be hitting numbers closer to 500, 750, or even 1,000 watt hours a kilo. It's important to remember coal, oil, they tend to be in the range of 5,000 watt hours a kilo. So there's a long way to go for us to hit great energy densities. But needless to say, these numbers are still very large. We need a lot of capacity to recycle batteries in the world. And as of today, we are barely sitting in hundreds of thousands of tons of capacity. So there's a lot of capacity that needs to be brought online if we truly want to ensure that we've got a clean, green source of energy. I'll go a little bit deep into the prevalent recycling technologies and their pros and cons and where is the world headed to with respect to recycling. The three primary recycling technologies available today tend to be what are known as the pyro process, the hydro process, and the direct process. The names are relatively indicative of what these processes are. A pyro process is a pyrometallurgical process, typically uses high temperatures. The hydro process is a hydrometallurgical process which involves a lot of chemicals. And the direct recycling process is a process through which we try to acquire or we try to extract the active cathode material and the active anode material directly. And broadly, the industry is trying to use one of these three, and some folks may be even using multiple of these in their processes. What's the sort of pros and cons of these three processes? If you look at sort of, I've tried to segment all the processes with respect to their economic efficiencies and in terms of their technical efficiencies here. Pyrometal is relatively the easiest of the process. The technology is extremely ready. It is not very complex. If I had to explain it very simply, it is about taking a battery and dumping it into a high temperature smelter and hoping various collectors will collect the relevant metals that go into the battery. The quality of recovered material is pretty low. The yields are pretty low because it is a high temperature activity. So needless to say, the emissions are not acceptable. And by and large, if you see globally what is happening, most people are running away from pyro processes because it is not a process that the customers typically appreciate. It also tends to be a very expensive process because the capital cost associated with setting up large temperature furnaces, large temperature smelters tends to be very high. So the world started moving in the direction of the hydrometallurgy process, a little bit more complex than pyro. It involved running a lot of chemical reactions to separate out the materials from each other. The recovered material tends to be fairly good, and the recovered material is typically classified as precursor material by the battery industry. The yields tend to be very good, but it is a complex process. It is a complex process, and it is a process where, while a lot of people are successful at lab scale, it becomes very difficult to be successful at industrial scale. The yields tend to be not as high as at the lab scale, and the pollutants tend to be typically quite high. This is a process that typically results in byproducts that are very difficult to do. And then the sort of what is known as the hopeful holy grail of the recycling process, where we enter into the direct recycling process. Direct recycling process is about ensuring that once we have liberated the active material from the cell casing, how do we separate the cathode and the anode material and make them available directly for a cell manufacturer, right? So, if I just take a simple example of the traditional cathode and active material, let's say I've got a lithium ferrophosphate battery, my cathode material is LiFePO4, and if I try to segregate that from my anode material, which is typically graphite, can I do that and then ensure that I upgrade my cathode and anode material to battery grade material? This is a technology which is probably not even at TRL 3, TRL 4 levels at this moment across the world. It is complex. Getting to a quality of material that is acceptable by the cell manufacturing industry has not yet happened. But this particular process to recover the material is probably the most efficient process if people can crack the entire technology here. Broadly, if you look at the recoveries from these three different processes, the pyro process tends to be the most lossy. Typically, lithium, manganese, and aluminum, which are present in the battery pack form, in the form of active material, in the form of current collectors, tend to be lost out in the slag. The hydro process tends to recover most of it, but globally, if you look at the yields that lithium in particular, which is a high value material, tends to be fairly low. Most people are not, while at a lab scale, most people are probably talking about 90% plus yields, but at industrial scale, I'll be surprised if anyone is sitting north of 70%, 75%. Direct recycling is the way to actually recover everything, both the cathode and the anode materials. So obviously there's no lossiness here, but getting to very high quality material is still a relatively distant dream. Come to a little bit about the recycling business models out there. We looked at a little bit about the recycling technologies available. But when you look at the business models available to us, there are companies operating across the entire value chain, right? There are companies which are nothing but pure collection companies. They collect end-of-life batteries. You've got companies which are refurbishing companies, which basically take a battery which is damaged, fix it, and then return it to the original application. We've got repurposing companies which actually take a battery, possibly fix it, may not even fix it, and put it out for another application than from the originally intended application. So a simple example is taking an electric vehicle battery and moving it into stationary storage. We've got a whole bunch of company business models on the recycling side, where we've got people producing different levels of end product. There are folks who produce what is known as black mass. There are folks who produce what is known as precursor, and there are folks who produce the precursor and the cathode active material. Obviously, these are at differing levels of scale and differing levels of commercialization. And then you've got integrated companies which are doing probably one or more of these activities in the value chain. And you see all these companies out in the market. There are many recycling companies that have emerged, not very surprisingly, given the volumes anticipated in this business. A little bit of commentary on what works for the recycling industry and what plagues the recycling industry. I think the easy one is what works for the recycling industry. It's a priority for governments. Needless to say, because of the geostrategic nature of the material, every government out globally, right? You talk about the developed world, you talk about the developing world, and you talk about the world that probably has not even started any significant access to lithium-ion batteries, are thinking about how to secure their resources. It's become a topic of hot debate across most legislatures in the world, and a lot of rules have been created, in particular within the US, California, the entire European Union, Japan, in India, and then the Chinese, of course, who probably have some of the most advanced rules that have been set up for recycling. The Indian government in particular published what is known as the battery waste management rules back in August 2022. Some of the most, again, I would really commend the government for producing what I would consider very progressive rules. These lay out extended producer responsibilities on people who actually place a battery in the market. And there are clear targets that have been defined for collection of these batteries. So that's a strong tailwind for the industry. Needless to say, because of that, and because of the anticipated numbers, capital flow has been fairly good into this industry, both from the private market as well as from the public markets. The large size of the industry is what is encouraging the strong capital flow. However, the challenges remain, and the challenges are fairly significant. And first and foremost, and this has classically plagued a lot of recycling industries not related to the battery sector, is the lack of standards. It's not very clear what recycling really is all about. It's not very clear what recycling processes should be all about. It is not very clear what repurposing is all about. There are no developed standards, very rudimentary standards, again, not just within India, but across the world. And I think everyone is struggling to figure out what really should a recycler be doing. So at this stage, it is acceptable. Everyone does everything, but that's not really the way we all want to go. So we obviously want to ensure that standards emerge around products, standards emerge around processes. As Professor Apparao's presentation aptly demonstrated, chemistries are changing by the day. At this stage, thankfully, most chemistries still tend to have a lot of lithium in them. But who knows how these chemistries will eventually evolve, right? Will potassium-ion become a chemistry of choice? Will lithium-ion maintain its dominance in various verticals? Or will hydrogen come and take over a very significant part of the industry? It is unpredictable, and typically when the chemistries and when technologies are fastly evolving, it becomes a challenge to actually put out capacity without knowing what exactly are you going to process. The recycling industry in general has never been traditionally organized. Again, not true just for India, but true global. There's a lot of material that flows into the informal sector. Anytime you're setting up a refining process or any factory, your primary goal is, do I have access to material, right? And if material moves into the informal sector, which does not have all the constraints of the formal sector, then typically it is tough to sustain a factory. The fourth question does become one of timing. I think at this stage, there are various predictions around when will the batteries actually come to end of life. Teslas have been doing fairly well for 12, 13, 14 years. No one truly knows, are we going to see large volumes in 5 years, 8 years, 12 years? So when do you actually go and set the capacity, right? Battery chemistries are only improving by the day. Cycles are only improving by the day. Already LFP batteries are offering 3,000, 4,000 cycles, which, quite honestly, if you're talking about one cycle a day, talking about 10 years, if not more than 10 years. And then you have to deal with the commodity market and commodity prices, which tend to move all over the place and can really hurt your business economics. So these are sort of the two pros and cons of the recycling industry. What are some of the new emerging areas from a technology and a concept perspective in lithium-ion battery recycling and battery recycling in general? I touched a little bit on the direct extraction of active material. It's not yet been commercialized anywhere very significantly. So an important area of research. But also another very important area from a business perspective is modularity of the recycling facility. Typically, when you have a chemical-based process or a temperature-based process, you want to run very, very large facilities to ensure you get economies of scale. But that does not work everywhere because you don't want to move these batteries around significantly. There is a very strong transportation cost, which hurts your economics. Transportation costs also become very critical because batteries are fundamentally hazardous. And there are a lot of strong regulations in terms of how do batteries move from one location to another location. People are trying to think, how can they create modular solutions? Chemicals are not something that anyone likes. So chemical is a sort of very, very broad encompassing term, but people are looking for solutions which do not generate chemicals. Unfriendly chemicals, particularly anytime you have a technology which involves leaching, sodium sulfate typically becomes a byproduct of a lot of leaching processes. So, and that does not have very significant uses. So how do you think of non-chemical based processing? There is an emerging area on the repurposing side where people are looking to mix different kinds of cells with different kinds of aging characteristics together to put out first battery packs. And then finally, OEMs and recyclers are collaborating to make recycling friendly battery packs for the market, right? Packs which are easier to recycle. One of the challenges that we face all the time in our recycling process is how to deal with potting material, thermal management material. Thermal management material makes the entire recycling activity extremely, extremely inefficient. I'll talk a little bit about the things at LOHUM for the next few minutes. So we actually run an integrated end-to-end battery life cycle management facilities. We have what is known as a battery dismantling facility, a battery reassembly facility, a battery materials facility, and then we've just initiated a couple of facilities where we've started moving into higher value alloys and higher value chemical materials, in particular, cathode active materials facility. These are all based out of Greater Noida. We are about 40 kilometers from New Delhi International Airport and are the largest integrated recycling and repurposing company in the country. We have at this stage capacities north of roughly 3 gigawatt hour equivalent of material that we can process. The core pillar of organization largely resides on recycling and repurposing. So these are the two technologies that we've been trying to really ace. On the recycling side, the core problem to solve is how to get very high yields at industrial scale with low capexes and low opexes. Ultimately, the idea is to maximize your return on investment, and that can only happen if you have high yields, low operating expenditures, and low capital expenditures. How do you do that? Is the core area of focus that we have. In particular, this becomes very important. If you look at historically what was happening in the lithium, cobalt, and nickel market, cobalt and nickel are relatively well-known metals, which have been broadly used by other parts of the other industries in the world. And so there was reasonable technology around separating cobalt or extracting cobalt from waste, extracting nickel from waste. Where the challenge typically came was when you had cobalt, nickel, and manganese mixed together, which is classically the case with lithium-ion batteries. How do you separate out all three? And that is a basic core engineering problem that everyone is solving. The second problem was of lithium. Lithium classically was not used in very large numbers, broadly by the ceramic and the glass industry, and to some extent by the pharmaceutical industry. And no one really cared about recycling lithium. And today, again, if you see, that is a big challenge that everyone is trying to work towards. How do they actually take out lithium at high yields and with high purities? If the lithium that you produce is not 99.5% pure, you really don't get much value for it from the market. And then you've got the broader problem. If you look at the broader set of chemistries being used, lithium ferrophosphate batteries have made a huge comeback in the last couple of years, particularly since Tesla started to evangelize it. Lithium ferrophosphate batteries do not have a cobalt or a nickel in them. The only material of value there is lithium, right? Is it truly viable? Can you truly recycle it? So those are the broad areas where we focused as an organization and developed a bunch of technologies to ensure that we are best in class. But even before we get to recycling, what we end up realizing is a lot of batteries actually can be repurposed, if not at the pack level, certainly at the cell level, right? And so when you talk about repurposing, the broader goal is how do you predict the remaining useful life? How do you actually, as a commercial organization, our goal is to actually warranty the remaining useful life. So how do we go about doing that? What are the kind of technologies? What are the kind of algorithms we create internally that helps us do that? We use a broad set of different processes based on physics-based modeling, empirical data-based modeling, and then certainly a little bit of data science, though there is still not extensive data available to ensure data science works efficiently. We also have developed a bunch of different applications which allow us to do these things more extensively. They've got a real-time battery pricing app, which talks with the battery management system to arrive at a residual value of the battery. We focus a lot on helping our customers understand how the batteries will be priced in the future at the time of buyback. That allows them to think about their own internal rates of return or their returns on investment on the battery. And the broad with which we are all working to ensure that we live in a world where everything is traceable and transparent, so that we are all larger goal of clean and green earth. So we try to communicate to all our partners what exactly has happened with the battery in terms of what did we do eventually with it, how much did we recycle, how much did we repurpose, and what were the broader carbon and water savings that came through it. Broadly, we focus a lot on R&D. Certainly, universities are always a step ahead of us, but we do as much as we can at the company level. And the three broad areas of R&D that we do are on the battery material side, on the cell modeling side, and on the financial and on the economic side, on a price modeling side for various materials that go into making a battery pack. So with that, I think I've covered most of the areas that I wanted to cover. Thank you so much for your attention, and I look forward to any questions.
Yes, that was a good presentation, Rajat. Thanks a lot for telling about your efforts in trying to put the batteries and trying to extract value out of these particular discarded batteries. I think there is a lot of queries and a lot of comments that are going to be there, but due to lack of time, I'll just take one. Would hydrometallurgy be economical if batteries move away from using cobalt and nickel?
So hydrometallurgy will be challenging, and the biggest challenge there is the price of lithium itself. Lithium right now seems to be giving us a fairly good price, ranging from 40, last year lithium hit almost $85 a kilo, lithium net. At this stage, lithium is sitting roughly at $38 to $40 a kilo. And lithium actually crashed a few weeks ago to $20 a kilo. Our broad math seems to suggest that once you're beyond $35 a kilo, you can run it sustainably. Anytime lithium goes below 35, and with lower quantums of nickel and cobalt, hydrometallurgy does become economically unviable.
Okay, that's nice. Thank you very much. So it is a possibility that we can look to.
Yes.
Yeah. Okay. So I think we have really been having a very interesting presentations by Professor Apparao and Mr. Rajat Verma. I would now like to pass over the stage, as I call it, to Dr. Venkatraman. Sushila, please.
Thank you so much. We've over the time that we've been running these webinars. We've had several discussions around energy, why energy is so important, and about generation and so on. And every time we heard why storage is just as important. And today we've had a good peep into that. As the world becomes more and more electric driven, we had Ravi Rajamani, who is in the audience today, who spoke about electric aircraft a few webinars ago. And, and the point did come up today about why, therefore, storage technologies are so important. And so Professor Apparao started by talking about what it is that has made it possible to get to where we are. And mainly that is improvements in energy density and lower costs. And a lot of that is because of the materials. So from there, he went on to talk about what other materials are being used, how they're being used, and the work that is being done in terms of improving storage technology. We are hitting the limit with respect to lithium-ion batteries, and whether it's because of finite reserves or because of how do we continue to improve energy density and continue to bring down costs. So questions like this are raised. We had a discussion around various materials, different substrates. There was a bit of a deep dive into FLGM-based graphene anodes, alloying-type anodes with sulfur-based cathodes, lithium-sulfur cells, and so on. So we looked at a lot of those technologies, and Professor Apparao, thank you very much for giving us those insights. Many of them, for those of us who are not in the field, was certainly an eye-opener. And then we learned that the third area that we have freedom to play around with is the electrolyte. And so using a combination of different kinds of salts and solvents, how do you arrive at a suitable electrolyte? And we saw in a fair amount of detail what was done by Professor Apparao and his various collaborators. And then there are other areas of research that are taking place, and we did look at some of them. Agri-based materials, the potassium-ion batteries, which many of our audience today have shown much interest in. And of course, the idea of the ferric source and Prussian blue cathodes, and how, if those kind of technologies actually become viable, we may end up with the supercapacitor not being required anymore at all, and we could just manage with batteries. And then we went on with Rajat to look at the battery ecosystem itself, how mining, which is the longest lead time activity, but completely unsustainable, and of course, refining as well, humanitarian issues, pollution issues, very high water usage, and so on, all of which defeats the purpose of going electric in the first place. So why the circular economy for batteries is so important. He also touched on raw material scarcity and how we're going to run out of, at the current rate of consumption and with the current kinds of technologies, in less than 20 years, we're going to run out of the materials. So then he went on to talk to us about the various technologies and also touched upon some of the business models around the recovery. So 3 primary technologies, the pyro process and hydro process, both of which are expensive and they have their own challenges. And then, so therefore, direct recycling seems to be a good way to go. But again, there is a long way to go in terms of building efficiencies in that space as well. We looked at business models around collection, refurbishment, repurposing, recycling, and of course, a combination of all of these. And challenges, which include the lack of standards, the changing chemistries, the existence of an informal sector, and of course, fluctuating commodity prices. And then we looked at some new concepts, such as non-chemical based processes, creating recycling-friendly battery packs, and then, of course, the need for a lot more research in direct extraction of active materials. And then, of course, we also had a peep into what it takes to run a firm such as LOHUM and do what LOHUM does. So I want to thank everybody. I want to thank Professor Apparao for a wonderful presentation today, for sharing so much about what is happening with respect to battery technologies. Rajat, for all that you shared with us about recycling, and Satish, for being a wonderful moderator today and accepting so readily to be part of this webinar. A big thank you to our audience for being here with us, and we look forward to seeing you on our next webinar. Goodbye.
Thank you very much, Sushila.
Thank you.